The next topic we want to look at is the Clausius inequality. To begin this, I want to go back to this idea of a heat engine operating between two reservoirs. So we have a high temperature reservoir here, TH, and we have a low temperature reservoir here at TC. And currently we have a Carnot cycle operating between those two reservoirs. So we were just talking about a Carnot cycle in quite a bit of detail, and we were coming up with an expression for the efficiency of that cycle. And we'll be using that expression here a little later on. So this Carnot cycle is getting an amount of heat from the high temperature reservoir, QH. It's producing work, WC, and that C refers to the Carnot cycle, and it's rejecting heat to a cold reservoir. Then the amount of heat it's rejecting is QCC. So there's two C subscripts here. The first one refers to heat transfer with the cold reservoir. The second one reminds us we're talking about the Carnot cycle here. The reason I have a little empty space over here is what we want to do is compare the performance of this Carnot cycle with the performance of some other cycle. So cycle A. So cycle A is meant to be a real cycle. Remember, the Carnot cycle is a perfect reversible cycle, can never do any better than that, whereas cycle A here is a cycle with some irreversibilities in it, so a real cycle. So the Clausius inequality, we're going to arrive at it by comparing the performance of these two cycles. Now, let's take a look at the energy transfers between this cycle and the surroundings. So first of all, this cycle receives QH from the high temperature reservoir. Now notice these two are intended to be exactly the same. So that's why there's no extra subscript on them. Those two QHs are equal. So what we're doing is we're feeding the Carnot cycle and cycle A exactly the same amount of energy, and we're going to investigate what happens to that energy in those two cases. So QH is common to these two cycles. The work produced by cycle A will be different than the work produced by the Carnot cycle. So we call that W sub A to remind ourselves we're talking about this cycle. And also the amount of heat rejected to the cold reservoir will be different. So QC, because we're talking about the heat rejected to the cold reservoir, but the second subscript is A because we're talking about cycle A. So this is the scenario we want to look at, comparing Carnot cycle to cycle A. Now this brings us to the beginning of the Clausius inequality. We're going to evaluate an integral around each of these cycles, and the particular integral that we're going to evaluate is the integral of delta Q over T. So remember what Q is: heat transfer with the surroundings, and T is the temperature at which that heat transfer is occurring. So it turns out that this particular integral has some very important properties when we apply it to thermodynamic processes. So we're going to take this integral and apply it first of all to the Carnot cycle, see what it equals if we evaluate this around the entire cycle, and then we're going to take it and apply it to that cycle A. And it turns out there's a difference in the value we'll get out of it, and that difference tells us something very important about the cycle. It allows us to characterize whether or not we have a perfect cycle. So we begin with the Carnot cycle. So we're going to integrate delta Q over T around the entire cycle. So just in terms of our notation here, you'll notice a little circle on the integral sign. That's a reminder that we're integrating around a complete closed loop, around a cycle. And the subscript C on here is to remind us that we're currently dealing with the Carnot cycle. So the first thing to realize is that because we're integrating around the entire cycle, we can split this up into 4 separate integrals, and each of those integrals is for one of the 4 processes. So that's the first thing that we'll see on the right hand side here, is we have split this integral over the entire cycle up into 4 parts: 1 to 2, 2 to 3, 3 to 4, and 4 back to 1. So that's the first feature of the right-hand side of this that we want to recognize. Now the next thing we want to do is remember some of the properties of those four processes that will help us to evaluate these four integrals that we have now. The first one is to remember that the process from 2 to 3 and the process from 4 to 1 are adiabatic. So delta Q is 0 for those processes. There is no heat transfer. So two of the four integrals on the right-hand side are going to be 0. We can do that right away. The other two processes, 1 to 2 and 3 to 4, remember that those are constant temperature processes. So what we've been able to do, and it's already shown up here in our notation, is we've taken the temperature that used to be inside of the integral and we've been able to move it outside. So 1 to 2 is happening at a temperature TH, and 3 to 4 is happening at a temperature TC. So we've got rid of two of the four integrals, and we've simplified the other two by recognizing their constant temperature processes. So that allows us to rewrite this integral around the entire cycle as QH over TH, because notice the integral from 1 to 2 of delta Q is QH. And likewise, the integral from 3 to 4 of delta Q is QC. And again, the extra subscript on there to remind ourselves we're talking about the Carnot cycle. So the value of this integral around the entire cycle, QH over TH, QCC over TC. Now here's where we want to revisit the expression for the thermal efficiency of a Carnot cycle that we just developed in the last lecture. So here's the result we got there. We found that the thermal efficiency is 1 plus QC over QH. That's actually valid for any heat engine. But for a Carnot cycle, we showed that that's equal to 1 minus TC over TH. Compare these two. We're saying there that QCC over QH must be equal to negative TC over TH. Just setting these portions equal to each other, and we're adding this subscript on here because we're talking about a Carnot cycle. So just rearranging this expression, moving the TC under here and the QH to the top on this side, we get QCC over TC equals minus QH over TH. Well, taking that and looking here, you'll notice that brings us to the conclusion that this is actually 0, because QCC over TC is negative QH over TH. So that is equal to 0. So what we've found here is that for a Carnot cycle, this particular integral of delta Q over T, when we evaluate it around the entire cycle, it's equal to 0. So that's a very important thing that we're going to make use of later on. But the value of that integral for the Carnot cycle is 0. And on this slide, we've shown why that's the case. Next, what we want to do is return back and do exactly the same thing over again, but for cycle A instead of for the Carnot cycle. So we turn our attention to cycle A, and notice in the title here I'm reminding us that this is an irreversible cycle. So Carnot cycle is a reversible cycle because it's made up entirely of reversible processes. Cycle A is an irreversible cycle because it has some irreversibilities in it. Friction, sudden expansion, whatever the source of those irreversibilities is. Well, we haven't said anything about what the processes that cycle A is using are going to be. In order to make this description or this development a little bit simpler, what we're going to do is pick a cycle A that is really not very much different than a Carnot cycle. It has one essential difference, but for the most part is very similar to the Carnot cycle, just so that this development is a little more straightforward, but it will not change the fundamental result. we're going to say that cycle A consists of the same four processes as a Carnot cycle, so two constant temperature processes and two adiabatic processes. The difference is not in that part of the description. The difference is for cycle A, those processes, one or more of them at least, is not reversible. Remember, a Carnot cycle, all four of those processes are reversible. Cycle A, it's the same processes, but with some irreversibilities. So that's the difference. So because we're using the same four processes, the beginning of this is very, very similar. Again, there are four processes, so we can break the cycle up into four integrals, one integral for each of the four processes. Two of them are still adiabatic processes, so those go because delta Q is going to be 0, so those portions are going to disappear. The other two processes are constant temperature processes still, so this simplification is still available to us. We can move our temperatures outside of the integrals because they're constant, and so we quickly get to the very same situation as we had for the Carnot cycle up to this point at least. So delta Q over T is QH over TH, QCA over TC. That's exactly the same as the Carnot cycle, except that we're talking about cycle A here instead of the Carnot cycle. Now is where we need to start comparing these two cycles to each other. So I've got our little schematic diagram back here to help us do that. Remember that Carnot cycle has the maximum possible efficiency. So we know that cycle A is going to have a lower efficiency than the Carnot cycle. So the efficiency of the Carnot cycle is bigger than cycle A because there is no cycle that can be more efficient than a Carnot because it has no irreversibilities. So that means because we're supplying these two cycles with the same amount of work, that means that the Carnot cycle is going to produce more work than cycle A. So this will be larger than that because it does a better job of converting heat into work. So that also means that the heat rejected for cycle A, so QC of A is going to be less than QC of C. Now the reason we're looking at QC there, if we just go back, notice the only difference in this expression from the one that we got for a Carnot cycle is this part right here. All the rest of this is exactly the same. So we want to know what is different about this between the two cycles. So that's why we're keying or looking at QC. So going back, we've concluded that QC for cycle A is less than QC for cycle C. This result might seem a little strange, so we need to be clear about why this is true. So I'm going to do that with a little numerical example over here. Remember I said that we are supplying the same amount of heat to each of these. So I'm going to say that QH is 100 units of energy. And it's the same in both cases. Doesn't matter what the units are, kilojoules, BTUs, doesn't matter. So 100 units of energy are fed to each of those cycles. Let's say that the Carnot cycle produces 60 units of work. So its thermal efficiency is 60%. Let's say that cycle A produces only 50 units of work. So this cycle is not as efficient. 50% efficiency here, 60% efficiency there. So that's fairly straightforward. Now what we want to do though is figure out what is QC for each of these cases. Well, remember our sign convention is important here, and also remember the sum of the Q's equals the sum of the works for any cycle. So let's look at the Carnot cycle. QH is 100, work produced is 60. So in terms of magnitude, we know that 40 units of energy must come out here because 100 goes there, 60 goes there, 40 goes there. But if the sum of the Q's is going to equal the sum of the works, and there is only one work, that means this QC is negative. So this is negative 40. So QCC is negative 40. And of course it needs to be negative because it's heat being removed from the cycle. So QCC is negative 40. Likewise over here, so if QH is 100 and the work is 50, QCA is negative 50. So notice that QCA is less than QCC because these are both negative numbers. Negative 50 is less than negative 40. So this little numerical illustration hopefully has helped you to understand how we got to that. So going back to our Clausius inequality, so this is what we have for cycle A, and this is what we have for the Carnot cycle. So if you look at these expressions, the only thing that's different between them is the heat rejected to the cold temperature reservoir. We're supplying each with the same amount of energy, and they're operating between the same two temperatures. So that tells us that the value of the integral, which is this, for cycle A is less than it is for the Carnot cycle. So this is the conclusion that we've come to, that this integral that we decided to evaluate, if we do it for any cycle, any real cycle, it's always going to come out less than it is for a Carnot cycle. And remember, the Carnot cycle was 0. So there's a very special property that this integral has, and that is that its value is negative for any real cycle, or any cycle that has any irreversibilities in it whatsoever. So this is what it's going to become. It is going to become a way to test cycles and see if they have irreversibilities in them. It's certainly not in that form yet. We've got a little bit of work to do to get it in that form, but this is the beginning of an analytic tool that we're going to use to test whether cycles and eventually individual processes have irreversibilities or not, and in fact measure how strong or how dramatic or how important those irreversibilities are. So the conclusion that we get to here is, notice we're going to combine these things together. So here I have that integral we've been evaluating, delta Q over T. Notice I've dropped the subscript here, so I'm now talking about any cycle whatsoever. Absolutely any cycle. And this is now an inequality, less than or equal to 0. So this is really just a way of combining these two things into one equation. If this happens to be a Carnot cycle, then it's the equality that is in play here, and that is equal to 0. But if this happens to be any real cycle, then its value is going to be less than 0. So the Clausius inequality says that the integral of delta Q over T is less than or equal to 0 for any cycle. So if you happen to look at a cycle and you evaluate delta Q over T around that cycle and you get a number bigger than 0, something is wrong. Either you made a mistake or there is something about that cycle that is impossible. Because notice what you're saying. If that comes out to a number bigger than 0, it means you've found a cycle here that has an efficiency even better than a Carnot cycle. So that there's processes in there that have less than 0 irreversibilities. So negative friction or something very, very strange like that. So this is going to turn in to an analytic tool for us to look at cycles and even individual processes to see if irreversibilities exist or not, and to determine whether those processes are possible or not. And notice this goes right to the root of the second law. Second law talks about a natural direction that processes happen, which makes certain processes impossible. Well, this is the beginning of a tool that will allow us to determine if processes are possible or not.